All right, welcome everybody to Intro to Space Navigation, Spring 2025, Lecture 10. I'm pretty sure it's Lecture 10 this time. Sorry about the mistake a few lectures ago, giving it the wrong number. So Lecture 10, and let me go ahead and share my screen. Here, stand by. Because we're about to review the course map. So some of you might remember the course. We talked about this a little bit last time too. So last lecture was matrix vector calculus, which kind of fits into this math category, although not exactly, because it's not estimation theory, but it is math. Today, we're going to be squarely in estimation theory. So this is going to be the mathematical framework for everything else we do in this class. So far, we've talked about, if you want to describe, for example, the position or attitude of a spacecraft, first you have to say in what frame, and then, okay, well, what is a frame? How do we define frames? At what time is a frame defined? But then you could say, okay, well, what about the relationship between frames? Now you have to talk about attitude representations. Or, okay, what about, the basic math and physics behind orbital mechanics and being able to propagate the state of a vehicle forward in time, that sort of thing, Kepler's equations. Then we talked about orbit determination, which are methods of estimation. So you're getting several partial states over time, and then you're ultimately doing a form of batch estimation to get the full state over time. Very nonlinear batch estimation, typically. Now we're getting into the math. So this is going to be more of like the wax on, wax off, or paint the fence for a Karate Kid reference, where for the next couple of lectures, it's going to be a little bit of just eating your vegetables. And then I think the fun stuff comes, especially when we get into the camera-based navigation and the Kalman filtering. I think that's kind of the dessert of this course. But right now we're eating our vegetables. So we're going to talk today about something called uncertainty quantification. But just want to clarify that, like, okay, we've done orbital mechanics. Now we're kind of at the bottom of things, looking into the math and the theory behind everything else. So, oh my, I see that when I prepared for this lecture, I didn't plug in my pen tablet. So stand by while I do that. But so uncertainty quantification is trying to answer things like, how well do we know our state? So a lot of what we're trying to do in this class, navigation, remember, is all about finding the state of your spacecraft, so position and velocity, given available measurements of your surroundings. And so then the question is, well, okay, we found an answer to our position or to our attitude or to our velocity. How sure are we? And you might say, who cares about that? We have an answer. It's like, well, if you're a navigator, you do care about that. That sort of thing does matter, because we need to be able to say, well, we think we're here, but we're really pretty sure we're in this region. You kind of bound, an elliptical or an ellipsoidal region of, well, we think we're in the middle of this, but we're sure we're in there somewhere. Right? And ultimately, that's really all we can say. You can never actually give a concrete answer to questions about your state. You can say, well, here's our state estimate, and here's our uncertainty. Kind of like giving a number plus or minus another. Same idea. So I'm going to talk today about, there it is, uncertainty quantification. So we're going to start by describing something called a random variable. So a random variable is a variable whose value, you know what, I can spell the word whose a little bit better. Sorry about that. Still working on adapting my handwriting. Whose value is subject to stochastic perturbations. Stochastic meaning random. So as the name implies, a random variable is a variable that is random. You can think of it as it is not a single fixed value. So instead, a random variable, or RV, is described by a probability density function, or PDF. PDF. There we go. So why do we care about this? This is a topic from estimation theory, but ultimately estimation is what we're doing in this class. We're estimating the value of your state, and we're treating the state not as a single number, but as a kind of an unknown on this continuum. Right? So a random variable is a fantastic tool for modeling something that we think we know, but we cannot be certain about. So for example, a spacecraft state. So a probability density function, or PDF, describes the likelihood of a random variable taking on a particular value. Now, because a random variable has to be something, the integral of the PDF must equal 1. So those of you that have taken statistics, which I think is probably almost all of you, are going to find a lot of today's topics similar to statistics. So we've learned about probability density functions, we've learned about mean, and probably also about standard deviation. We're definitely going to talk about that today. And basically, today's lecture is statistics applied to vectors. So what is the mean and standard deviation of something that we don't know that is also a vector, like the position or velocity of a spacecraft? So it stands to reason that if we're describing the position of a spacecraft with a random variable or a vector of random variables, then the integral of that distribution has to be 1, because the spacecraft has to be somewhere. Right? There's no way that it's nowhere. It has to be somewhere. That's kind of the idea. So we'll say the integral from negative infinity to infinity of P of z dz is equal to 1, where P of z is the probability density function describing a random variable z. So in this case, I'll make this a little bit more explicit here. The capital letter denotes the variable itself, and then a lowercase letter denotes a particular instantiation. Or a particular realization. Right? So the idea here is it's a little bit like probability examples where it's like Susie has a bag of marbles, and she can draw from the bag of marbles, and it's either going to be red or green or blue, and then find the probability of this. You can think of the bag of marbles as the random variable. So there's some distribution, could be green, could be red, could be blue. But then once she actually reaches in and grabs a marble, now it's a lowercase letter. This is a particular instantiation. On this day at this time, we actually did the test. We really did pull a marble from the bag, and it was this, right? So the lowercase letter is a realization of the uppercase letter, which is kind of like the situation. All right. So one of the first tools that we're going to use, and this will come up for the rest of the course, is the expected value operator, which some of you might be familiar with. So next, we introduce the expected value operator. That looks like E of something. We usually use brackets. So what is the expected value of Z in this case? And this would be capital Z. The expected value of Z can be computed according to the integral from negative infinity to infinity of Z times its own probability density function, dz. So E of Z is the expected value of Z, sometimes called the first moment or other times just called the mean. So on average, if we pull a marble from Susie's bag of marbles, it's going to be red, right? Because that's something mathematically about the distribution underneath the number of marbles in the bag means that on average, when you pull a marble, it's going to be red, that sort of thing. On average, our velocity is this. This is the mean. So this would be, in the case of a bell curve, this would be the center of the bell curve, that sort of thing. All right, that expected value operator. First, we can observe that the expected value is a linear operator. So I'll leave this as an open question. Somebody who probably has taken, I think, systems analysis techniques with Dr. Mishra, he goes into great detail on this, but what does it mean for something to be a linear operator? Is that like, besides just based on vibes, do we have actual mathematical tests for that?
From my memory of SAT, it's that you can take there's certain qualities that it has. So like if you multiply a constant by that operator, right, it'll still equal the same value, the value of the function times the constant,
Yeah, it's
right?
like scaled input gives you a scaled output, that sort of thing.
Yeah,
Yep.
that sort of a thing.
And then also, I think you should be able to do 2 inputs added is the same thing as the function applied to, like you can either apply the function after you add the inputs, or you can apply the function to each input and then add. Now, if I remember the fancy terms, I think it's superposition and homogeneity are the actual terms, but this is how I have it memorized. The expected value of some scalar A plus some scalar B times a random variable Z is A plus B, or sorry, too fast. You could split it up. So this is the expected value of A plus the expected value of Z. But then this is the same thing as the expected value of A, which is just the scalar A in this case, plus B times the expected value of Z, which is just A plus B, expected value of Z. Right? So linearity means you can split up the inputs. You can apply the function before or after addition and it still works. You can apply the function before or after scaling and it still works. And in practice, when we're writing out some big nasty function and we say, okay, take the expected value of this, before you despair, recognize that the expected value only applies to the random variables in that string of numbers and letters. So some scalar A where we actually know what that number is, and some scalar B, the expected value just ignores those, and it applies to a random variable Z in this case. All right. Note, so let's just write this out and make it clear. Note that the expected value of a non-random variable is itself. So the expected value of the number 4 is just the number 4. It's kind of a moot point. Why would we even talk about it? All right. So maybe if you're familiar with statistics, we've talked about mean. The next thing is standard deviation. So we're going to build up to that. So you could say if the expected value of Z, which we'll often say is equal to mu, is the first moment of Z about the origin, then we will define lambda sub k as the kth moment of Z about the mean. So the way we would write this is the expected value of, and then in parentheses, Z minus mu sub k to the power k. That is lambda k. And that is just the integral from negative infinity to infinity of Z minus mu to the power k, probability of Z dz. So that's the actual function for this. But we'll see how this actually applies for first moment, second moment, third moment, so on and so forth. So by definition, lambda 1 is equal to 0. And the second moment of Z about its mean is called variance, which should ring familiar if you've taken statistics before. So let's go through and actually write out an equation for that. The square root of variance is called standard deviation. So maybe this is sounding familiar, that a certain probability distribution has a mean and a standard deviation, and you can almost visualize, for a bell curve at least, this particular value is 2 standard deviations away from the mean, that sort of thing. So hopefully those terms are sounding a little bit familiar. Standard deviation, we say, is sigma. So sigma squared is our variance, and that is the expected value of Z minus mu squared. And that is the integral from negative infinity to infinity of Z minus mu squared, probability of Z dz. And hopefully it stands to reason, you can never have a negative standard deviation, right? So if Z is a random variable, not only that, you can never have zero standard deviation, right? There's always going to be some uncertainty. So that is, the variance is strictly a positive number. Right? And briefly before we move on, so we'll have a natural stopping point in 1 second here. We should also acknowledge higher order moments. So skewness is the third moment. And it deals with asymmetry. So think of a standard bell curve. There is no asymmetry, right? But you could also imagine a probability distribution that is not a bell curve. It's some sort of lopsided distribution where it's more likely to be over here than it is over here. That would have some detectable skewness. The fourth moment is called kurtosis. Sounds like a terrible disease. Kurtosis is the fourth moment. And it deals with peakedness, or the pointiness of the distribution. Peakedness. You know what? I kind of messed that up. I'm going to try to write it again. Anyway, the main takeaway from this portion of the lecture is we can have a random variable. That random variable has a mean and a standard deviation. We have not introduced the bell curve yet. We have not talked about a Gaussian distribution. We've not even talked about random vectors yet. So this is all pretty basic foundational stuff. So questions so far? All right, cool. So now it's time to talk about some actual realizations of this stuff. So we're going to talk about two common distributions that we will use in spacecraft navigation. Next, we introduce two common distributions used in spacecraft navigation. The first is a uniform distribution, and the second is a Gaussian distribution. Both of these should be familiar. So the uniform distribution is handy when you have no knowledge between two extremes. So you could think of it as, okay, a graph where on the x-axis you have some values, and you know that your distribution is between A and B. So this would be the random variable. And then the y-axis is the probability of that random variable taking a specific value. Well, the uniform distribution is just a rectangle. Right? So we make a rectangle between A and B such that the area under the curve is 1. And that's it. So the way we would write this is the probability density function of Z is 1 over B minus A in the case that Z is between A and B, and then 0 elsewhere, so 0 otherwise. And so now the expected value, hopefully this makes sense. if you know that your variable is something between A and B and you know nothing else, so it's an equal distribution, equal probability of any number between A and B, then on average, your answer is going to be halfway between A and B. Because half the time you'll pick something closer to A, half the time you'll pick something closer to B. So should be pretty straightforward, and you can actually go through and write out, do the full integral if you want to. But the expected value of this random variable is A plus B over 2, or the average of them. And the standard deviation, if you go through and crunch the numbers, is B minus A squared over 12. Now that one, a little bit less intuitive, but if you just go through, pop it into the equation for variance, you'll get the variance is B minus A squared over 12. All right, pretty straightforward. The Gaussian distribution should be even more familiar, and we're going to spend a lot of time on the Gaussian distribution in this class. We'll talk about why later. So the Gaussian distribution also called the normal distribution, is most commonly used in navigation. And here I go trying to draw a Gaussian distribution. We'll see how this goes. So you've got Z and probability of Z, and not terrible. I'll take it. So in this case, the peak value is here. This is meant to be symmetric, so just take my word for it. And then also, let's say over here, you've got some inflection point where things inflect from upward facing to downward facing. And then over here on the other side, you've got that same inflection point. All right. The center of the peak is mu, and the inflection points are the one standard deviation. So mu plus sigma, mu minus sigma. So plus or minus one standard deviation. And you might be familiar between, what is it? I think it's 62% of the distribution is between plus and minus one standard deviation, and then 95 and then 99 based on the others. I'd have to go through and pull out the exact numbers, but hopefully this looks a little familiar. The equation for Gauss's distribution is the probability of Z is 1 over the square root of 2 pi sigma squared, and then exponential function of negative 1/2 Z minus mu over sigma squared. And that should look a little familiar as well. You might also be familiar that the Gaussian distribution, or the normal distribution, is generally centered at the origin and is set up so that the area under the curve is 1. So the way this is set up, if you change the sigma, the standard deviation, the whole thing gets wider or narrower, but it also gets shorter or taller so that the total area under the curve is 1. If you wanted to give this an arbitrary peak, then you could just do away with this front matter here and just have some number times this expected value. But as it's set up right now, this is really beautiful, such that the integral of this curve is 1 regardless of sigma. Now, this is a lot, and I'm not going to go writing this again several times. In fact, I might never write this again exactly as it's written. We're going to introduce the shorthands that Z is distributed as, sorry, it's meant to be a tilde, is distributed as a normal distribution. Try that again too. It's meant to be like a fancy n. Normal distribution with some mean and some standard deviation. So this is distributed as. And you'll see this come up in homework assignments. All right. So we'll note that the Gaussian distribution, or the normal distribution, is described entirely by its mean and standard deviation. That's my abbreviation for standard deviation. So you don't need any more than these 2 degrees of freedom, mu and sigma, to describe this function.
I just have
So,
a quick question. On the exponent, is that a 1 over z or 1/2?
oh, sorry, yep, 1/2. There you go. Maybe that's more clear. There you go. Thank you. Yeah, I realize Z and 2 are difficult for people who have good handwriting. So you're basically cooked in this case. But thank you. So the Gaussian PDF is commonly used for a few reasons. First is that it is easy to define. So it's got 2 parameters. The next is it has desirable mathematical properties. So for example, the Fourier transform of a Gaussian is another Gaussian. Which is kind of neat. Another is that Gaussian distributions remain Gaussian under linear approximation. But the big one is central limit theorem. Which says that the mean of a sufficiently large number of independent random variables will approach a Gaussian. So this is why a lot of non-Gaussian things come together and create a Gaussian. That's the idea. So there's this idea in mathematics that if you have some random effect, which is not a normal distribution, and then some other random effect, which is not a normal distribution, and then some third random effect, which is not a normal distribution, and you just keep adding random effects. It's like, well, the probability of this event depends on these million things, which none of them on their own follow a normal distribution. In aggregate, the net effect will be that your final answer appears Gaussian. So you get enough randomly distributed functions together, and then in aggregate, they look like this, which is pretty cool. I want to highlight that there is a great 3 blue, 1 brown video. I know I keep recommending that channel. It's a great 3 blue, 1 brown video on the central limit theorem. Really highly recommend that YouTube channel for anybody that wants to know more or kind of drill down into the theory behind a lot of this stuff and make it make intuitive sense. So yeah, central limit theorem, 3 blue, 1 brown video. But basically, this is why the normal distribution is so ubiquitous in nature, right? I mean, so many things, people's test scores, people's heights, that sort of thing. are distributed along this Gaussian. It's a fantastic tool. So if you've taken statistics, you've definitely learned about this normal distribution. So just say one more thing. In practice, a lot of non-Gaussian things contribute to error. So error itself right? So there's a good checkpoint. The next thing I want to discuss is what if your random variable is not a scalar, but it is a vector? So questions on anything we've learned up to this point? All right, going to burn through one more page of notes and then we will take a little break. So our next topic is random variables as vectors. So the concepts of mean and standard deviation can be extended from scalars to vectors. So you might be imagining in your head that a probability can exist in some higher dimension, right? Like instead of having one input, the number line z, and one output, the probability of z, which is kind of like a one-dimensional thing, you can imagine a two-dimensional thing where you've got the probability of some combination of x and y, or even the probability of some combination of x and y and z. And maybe it makes sense that if the space that we're operating in is a random vector, then the mean of that random vector is a vector. Maybe that makes sense. Like on average, our position estimate is this, right? But it might be a little bit harder to imagine the uncertainty that scales up into a higher dimensional space. And so that's really what we're going to be spending some time on today, is this idea of standard deviation in higher dimensions, which is pretty nifty. There's a cool word for it, but one thing at a time. Just wanted to kind of preview where we're going. So let's say that we've got some random vector z, which is some z1, z2, all the way to zn. And this is a column vector. Then the mean of this random vector is mu, which itself is also a vector. Well, that is just the expected value of z. And that is the integral from negative infinity to infinity along the nth dimension, and then the integral from negative infinity to infinity along the n minus one dimension, all the way to the integral from negative infinity to infinity along the first dimension. Z as a vector, probability of z, dz1, dz2, all the way up to dzn. So this is imagine you've got two-dimensional integrals, three-dimensional integrals. This is going to be an nth dimensional integral. So you could go through and actually crank out this computation, but we will never do that in this class, so don't worry about that. You can just think of it as mu, the mean vector, is the mean value of each element in the random vector z, right? So mu is the mean. Oops, sorry. I'm too excited erasing things. Element. So hopefully that makes some sense. You can imagine a higher dimensional distribution. On average, it's got some value. That value is a vector in a dimensional space. Not too confusing, hopefully. Variance becomes a bit more complicated. So you can imagine that if your random vector has a mean that is a vector that is n dimensions long, your random vector's covariance, or your random vector's variance, is going to be a matrix which is n by n, where we talk about the uncertainty along each axis, but then also the relationships between the uncertainty of each axis. So you've got your x uncertainty, your y uncertainty, your z uncertainty, but then also your xy uncertainty, your xz uncertainty, and your yz uncertainty. So I'll write that out in a second here. So we must consider the variance of each vector element, and I slipped and said the quiet part out loud. We must also consider the covariance between each pair of vector elements. So the variance of a random vector z is a symmetric, positive, semi-definite matrix called the covariance matrix. That word covariance is really the word of the day today. That's the big thing I want you to remember. So we're going to talk a bunch more about covariance in a minute. But also, as I'm writing out the next thing, does someone want to take a stab? What does a symmetric positive semi-definite matrix mean?
Symmetric basically means that whatever's like above the diagonal is the same as whatever's below the diagonal, right? Like it's kind of flipped. Positive means that the determinant of the matrix is positive. And semi-definite means that it's possible that some of the vectors are not like, it's possible that it's not completely defined. So some of the vectors could be linear, like I'm saying linear, but I don't mean linear sort of thing.
Yeah, that's pretty much right. They hit the nail on the head. What I think of as positive semi-definite is that it might have, if you did an eigen decomposition, it might have some zero eigenvalues, but it will never have a negative eigenvalue. Or you could think of it as the covariance matrix, in my mind, describes a shape in n-dimensional space. And that shape will always either have a positive volume or no volume. So it's flat along some dimension, but you'll never have like a weird negative volume, if that makes sense. So we'll kind of get into what that means a bit later. But yeah, very good. So it's also positive and symmetric as well. So you'll never have negative uncertainty, and then also your xy uncertainty is the same as your yx uncertainty. So it's going to be symmetric about its diagonal. So the probability of this particular vector z, or sorry, the covariance, we use the p for covariance in this case, capital P is covariance, is a giant matrix which looks like the expected value of z1 minus mu1 squared, and then you've got the expected value of z1 minus mu1 multiplied by z2 minus mu2. But then over here you have the expected value of z2 minus mu2 multiplied by z1 minus mu1. Over here you have the expected value of z2 minus mu2 squared. And you can imagine this scaling out so that it is an n by n matrix. Or for shorthand, we can say that this is the z1, so this is the z1 direction, the variance along the z2 direction, on down the line, the z1, z2 covariance, and the z2, z1 covariance. So you can think of it as the xy uncertainty and the yx uncertainty, that sort of thing. Diagonal terms are called variances, and the off-diagonal terms are called covariances. And this altogether is called the covariance matrix. So for the rest of the class, we're going to be saying things like our position is unknown, but our estimate of our position is some value, and our covariance is this other value. So the covariance is the higher dimensional representation of the error bars that you might say. You could say, okay, in a one-dimensional case, the range from spacecraft A to spacecraft B is 100 meters plus or minus 5 meters, right? So in a one-dimensional case, you just need the one number. In a three-dimensional case, you need a 3x3 matrix to describe your uncertainty in your position. So there's how much we're not sure about its x direction, how much we're not sure about its y direction, its z direction, and then the x, y, yz, and xz off diagonal terms. Now, one more thing, and then I think we're ready for a break in a moment. We can also say that sigma zi zj is some rho ij sigma zi sigma zj. So the covariance between the ith and the jth term is the same thing as the standard deviation of each of those terms multiplied together times some what's called a correlation coefficient. So you can imagine 4 cases here where you've got, now we're just going to talk about correlation. So this should look a little familiar. Let's say this is Zi and this is Zj. Let's try to clean up that J a little bit. And I'm going to cheat. I'll slow down in a minute, make sure everybody has time to get caught up. But basically, if your data cloud is just this complete random noise, then you would say, and I guess I'll kind of circle all this. If there's no particular correlation here, you would say that your correlation coefficient is basically 0. So rho zi zj is basically 0, or there is no correlation. So if one of your off-diagonal terms is 0, then you would say that the ith and the jth term have nothing to do with each other. Along this axis, there's no correlation. You could also have some sort of a positive correlation, just to say that an increase in one axis means that you'll likely increase in the other axis. So in this case, your rho zi zj is a positive number. This is positive correlation. So we saw an increase along the x direction. We will likely also see an increase along the y direction. These two terms have something in common. Knowing something about one tells you a little bit about the other on average. This could also go the other way. Where rho zi zj is negative, should be negative correlation. So whenever we see I go up, j goes down. And then you could also imagine something where your correlation is so tight. In this case, your rho zi zj is equal to 1. This is called perfect correlation. So whenever in statistics your correlation between two variables gets too high, like it's something like 1, that tells you that you might actually not be measuring two different things. You might be measuring the same thing discussed two different ways. So you can think of it as, I guess this is a wacky example from statistics, but imagine if you asked 100 people how tall they were, and then you asked 100 people, well, if they laid down on the ground, how long are you? Like, that's not really two different questions, right? Like, everybody who says that they're 5 feet tall are going to say that they're also 5 feet long when they lay down. It's the same thing. So whenever your correlation gets high enough, you should be a little suspicious, right? Typically, in practice, we may see some correlation closer to what we see here in the middle, the positive and negative correlation cases. You could also have something that is just a circle, but it's often a circle or an ellipse. If it gets close enough to a straight line, I don't often see that in practice. So, but that is, mathematically speaking, perfect correlation. Okay, so I think that is a good halfway point, and we've been going at it for about an hour. Again, apologies, this is going to be a little bit of a longer lecture, but we've got a lot of stuff to get through. Should be a little bit better after this. Let's go through and take a 10-minute break, and then we'll keep on burning through the rest of our material here. So it's, what, 6:58 for you, so we'll say break, back at 7:08. All right, welcome back. We'll continue our discussion of random vectors. And we'll wrap up with a couple numerical examples, which hopefully make this make a little more sense here. So I'm going to try to speed up a bit because we're halfway through the notes and more than halfway through our time. So let's see. The PDF, probability distribution function of a Gaussian random vector is, this is going to look a little familiar. Probability of z is, okay, so remember for a scalar, it's 1 over square root 2 pi sigma squared, or 1 over square root 2 pi variance, right? In our case, it's going to be 1 over 2 pi to the power n over 2. So for a one-dimensional, n equals 1, then we're right back to where we started. And then instead of the standard deviation, we're going to use the determinant of the covariance matrix P, but same idea here, to the 1/2 power. And then all of this is multiplied by the exponential function of negative 1/2. And for the scalar case, it's z minus mu over sigma squared. So you're basically saying the distance from this value from the mean scaled by the standard deviation. Well, the way we do that in vector land is we say the vector z minus the vector mean transpose, and then instead of 1 over sigma, it's the inverse of the covariance matrix, and then z minus mu again. It's the idea. Or in shorthand, we would just say that the vector z is distributed as a normal distribution having a mean of the vector mu and a covariance of the matrix P. All right. Now, the exponent, or the thing that goes into the exponential function, we're going to call this phi of z. Phi of z is z minus mu transpose P inverse z minus mu is called the negative log likelihood function. And the square root of the negative log likelihood function is called the Mahalanobis distance. Which sounds fancy, but all this is what we were talking about before. Distance from mean weighted by standard deviation, or in this case, it's distance of the vector z from the vector mean weighted by inverse covariance. So same concept in higher dimension. Now, this next part should hopefully, it's going to sound, we're getting even fancier and fancier, but this is about to turn back into some concrete stuff fairly shortly here. So bear with me. For a given distribution, there are a family of values of z. So there's a whole bunch of random vectors or instantiations of a random vector that can occur with the same likelihood. Now here's where we get fancy. These values, these vectors, form a surface in n-dimensional space. Now, continue to bear with me, because it's going to get weirder and weirder until we draw a picture. Since P is positive, semi-definite, this surface is an ellipse, or ellipsoid, in n dimensions. So ellipsoidal surfaces of constant probability are described by all values of z such that the Mahalanobis distance, so z minus mu transpose p inverse z minus mu, or in this case, the Mahalanobis distance squared is k squared, or the Mahalanobis distance is k. So the resulting shape is what's referred to as a k sigma error ellipsoid. All right, that's pretty weird. Let's make it make a little bit more sense. So I'm going to go through and draw 3 examples of this. Hopefully it'll start to click. So we'll do case, two-dimensional case, and then a 3-dimensional case. Pretend there's a origin point there. There we go. Okay, so let's start with a simple bell curve. Okay, and so imagine this is mu, and I'm going to use 3 different colors here. Let's use maybe orange, and then green, and then blue. So as drawn, maybe this is our 1 sigma, and then I'm not going to draw this exactly to scale, but let's say there's our 1 sigma values, our 2 sigma values, and then even further out in blue would be like our, maybe I'll use like a lighter blue, our 3 sigma values. Is that, oh, sorry, I'm painting in like galaxy colors here. So in case of orange, this would be the 1 sigma. So it's not an ellipse just yet because we're at too low of a dimension to see it. But the idea is that this point over here and this point over here have the same probability of happening. And then similarly, this point over here and this point over here also have the same probability of happening. They're the 2 sigma line. And then similarly over here, you've got the 3 sigma line. And we typically think in terms of there being an interior to this, right? So the probability of something being within 1 sigma is some value, within 2 sigma is some value, within 3 sigma is some value. But the way I like to think of this is that it's almost like contour lines in some n-dimensional space. Okay, So this is something where, in this case, z is the only thing that we're considering. It's one dimension, and this is the probability of z. Now, we start in one dimension because we're about to go up into higher dimensions. Imagine here that we're looking at z1 and z2, and probability of z is out of page. You get the idea here? So in this case, imagine that it's like a mound that's coming out of the screen towards you here. Well, then in this case, we might face something where there's some uncertainty here, which this is the 1 sigma ellipse. And then there's some uncertainty and this is the 2 sigma ellipse. And then maybe this is the 3 sigma ellipse. You get the idea there. So in this case, it is a mound, and then 1 sigma, 2 sigma, 3 sigma are contour lines on a map. I think that's the best way to think about it in 2 dimensions. And now we can also extend this up to 3 dimensions. And you might say, why would we bother with 3 dimensions? Well, that's going to come up in this class, right? So in this case, this is Z1, and then this is Z2, and then this is Z3. In this case, it's even harder to imagine, because now if you've got 3 inputs and 1 output, that's a 4th dimensional function, which I can't really plot all that well. But if the contours of constant probability are just points on a number line, or they are ellipses in 2D space, then they form ellipsoids in 3D space. And so maybe the 1 sigma ellipsoid might look like this, with some cross section that looks like this. This is meant to be like a football shape, if that makes sense. And then you can go through and say, okay, well, 2 sigma, oh, wrong color. Thought I was on green. Two sigma would be a larger football shape. And then 3 would be a still large ball. So now our contours of constant probability are surfaces in 3D space. Pretend those are all drawn. Probably do a little bit better, but you get the idea. And then this would be okay. You know what? I am going to try slightly harder. I think I can do better on green and blue. All right. Apologies. Yeah, my handwriting is like worse than usual today. We can do better than that. Hopefully you get the idea across that we're trying to get through here. So this would be uncertainty here. This would be our uncertainty here. So maybe that's just a little bit easier to work with here. But this is meant to be a 1 sigma, a 2 sigma, and a 3 sigma surface. So 1 sigma, 2, 3 sigma. We won't go any higher than this. And also it's worth mentioning that as drawn, all 3 distributions have 0 mean, right? So you can imagine then when we're talking about something like a spacecraft position, we would be operating in this 3rd space here, where we'd say, well, we're really pretty sure we know where it is. That's our best estimate, but we can't say with 1,000% certainty. But we can say that our uncertainty in our spacecraft position is described by this football shape. We are a certain amount sure that it's within the 1 sigma football. We're even more sure that it's in the 2 sigma football, and we're even more sure that it's within the 3 sigma football. So the idea that we're describing our position or our velocity or our attitude covariance, and we can visualize that as like contour plots in n-dimensional space, or these kind of potato or football shapes, that we know we're within that area. That is kind of a common theme moving forward in our state estimation problems. So I like to think of it as, in the 1D case, we have points equidistant from the mean. In the 2D case, we have ellipses, or I think of it as like a dartboard. So we're aiming for the bullseye, but we're really pretty general, right? That's the idea. And then in the 3D case, we've got a ellipsoids. Or I think of this as, if you're familiar with Russian nesting dolls. You've got some 3D shape, and then a larger 3D shape, and then a still larger 3D shape. All right. And then similarly, in the 1D case, 68.3% of the distribution. Oh, actually, you know what? Sorry. Start a new bulleted list down here, because I think this is going to get confusing here. For a one-dimensional Gaussian, 68.3% of the distribution lies between the 1 sigma line. So this orange region is 68.3% of the distribution. Now for the 2 sigma, so the green region, this would be 95.4%. And then for the blue region, this would be 99.7%. Is the 3 sigma region. So just to be clear, this is this. This is this. This is this. But that is true for the 1D case. Okay. This only true in 1 dimension. In the 2D case, .3% of the distribution lies within the 1 sigma ellipse. And then for a 3D case, we only have 19.7% of the distribution lies within the 1 sigma ellipsoid. Okay, so what's going on there? I like to think of it this way. We'll look at a 2D case. So let's say this is Z1 and this is Z2, and let's say that our mean value is right here. So we've got some mu1 and you've got some mu2. Then let's also say that you've got this distribution where maybe this is our 1 sigma ellipsoid. which I'm trying to draw pretty darn close to a circle in this case. Or you know what? See if lightning can strike twice. This is our 1 sigma ellipsoid. And then maybe we'll draw our 2 sigma ellipsoid to get the idea here. Okay. So in this case here, maybe I'll go back to orange. This is 1 sigma, or the 1 sigma bound in 1 dimension. And then similarly, this is the 1 sigma bound in the other dimension. But if you project this over, you get, okay, well, that's meant to intersect. Maybe I'll go back and do it this way. You can see how as you get to higher dimensions, sorry, there we go. And less of the distribution is caught within this region. So here, between 1 sigma and positive 1 sigma and negative 1 sigma, and the 1 dimension, you catch this amount. But it's kind of like the inscribed circle problem, right? You're losing these corners. So as you go into higher and higher and higher dimensional space, trying to say, well, okay, how much of this distribution is within the 1 sigma ellipse, or in this case, circle, or how much is within the 1 sigma ellipsoid, it gets to be less and less and less. So that's something to be aware of. We would not say if you have the 3 sigma ellipsoid, you are 99.7% certain of your position in 3D space. It's not how that works, right? So just be careful there. You don't want to go off being overconfident or sounding silly in that case. But in this case here, this is 68.3% of the distribution. And this is 68.3% of the distribution. But then within here, it's only 39.3% of the distribution. Okay, and with that, I've got one numerical example to wrap us up here, and that is on eigendecomposition. Which is a fantastic tool for looking at higher dimensional covariances. So given just any arbitrary n by n covariance matrix, T, how does one plot or interpret this? So you can think of, consider the 2D example. Where the covariance is 9, 0, 0, and 4. And you might immediately notice 9 and 4 are both perfect squares. And I did that on purpose because I'm lazy. So we can determine some things by inspection. So first of all, there is no Z1, Z2 correlation. The XY correlation is 0. So what does that mean? Means ellipse aligns with the Z1 and Z2 axes. So we're going to have an ellipse where its long axis is along X and its short axis is along Y, or vice versa. We don't necessarily know yet, but we know it is not diagonal. Okay. We also know that sigma 1 is square root 9, which is 3. And sigma 2 is square root 4, which is 2. Okay, so we can go through and plot this just by hand. So we'll do a little number line here. Let's say 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So our 1 sigma ellipsoid goes from 3 to -3 on the z1 axis, and from 2 to -2 on the z2 axis. So we're kind of from here to here to here, and then from here to here, here. And there's our 1 sigma. And then similarly for 2 sigma, it would be from 6 to 4 to 6, like that. So here's our 1 sigma ellipsoid. Here's our 2 sigma ellipsoid. And you can imagine the third one, just kind of too lazy to go through and do that. You get the idea. Now, this was very straightforward. How do we handle a P matrix with off-diagonal terms? We don't. We do eigendecomposition. So, I mean, your calculator could go through and do this, but if you wanted to try to understand what's going on with a P matrix that has off-diagonal terms, then what we would do is eigendecompose it into a covariance matrix in some useful frame, some principal frame, and then a set of matrices which map into that principal frame. So eigendecomposition will tell us the variance in the principal frame. Those are our eigenvalues. And how to map into this principal frame. And those are our eigenvectors. So you can think of it this way. Let's say there's some vector z prime, which is just rotated z. Okay. Then the covariance associated with this, so the p prime, would be the expected value of z prime minus mu prime, z prime minus mu prime transpose. Okay. But then we also know that z prime minus mu prime is just tz minus t mu, which is to say it's t z minus mu. So we can do a substitution. P prime is the expected value of the matrix T times z minus mu, and then z minus mu transpose T transpose. But remember that the expected value operator only applies to the things that are random. And this matrix, this T, this attitude transformation matrix, is not random. So you can move it outside. You could say that it is T expected value of z minus mu transpose T transpose. So the T moves outside. But now, isn't the expected value of Z minus mu transpose just P? So you could say that P in the new frame after a rotation is T, P in the old frame, T transpose. So that is to say, if you want to take a matrix and move it from some old frame to some new frame, you have to left and right multiply by this attitude transformation matrix T. Okay. If this seems kind of weird and arcane, we're going to go through an example in a moment here, which is going to make things make a bit more sense. So let's set up our eigendecomp problem. So we'll say P, and we're going to use the vector U in this case. P ui is equal to lambda I ui. But in this case, we can say that this U direction is actually a unit vector. So we have P ui unit vector is equal to lambda I ui unit vector. So there's an arbitrary scale. Because the scale of U is unimportant, we can just treat them to be unit vectors. So you can say that P multiplied by some unit vector 1, some unit vector 2, all the way out to some unit vector n is equal to, so now this is going to become a matrix. That's the same as unit vector 1, unit vector 2, all the way out to unit vector n, multiplied by a matrix of eigenvalues, lambda 1, lambda 2, all the way down to lambda n, with zeros on the off diagonal. Or P times the matrix capital U, which is just all these vectors scaled, is capital U times capital lambda, which is just a square n by n matrix with lambda along the diagonals. Okay. Well, then you could just as easily say PU is U, or sorry, got ahead of myself. We're going to right multiply by U inverse. So we get P is equal to U lambda U inverse, or U inverse PU is equal to lambda. So why do we care about this? Well, lambda is the eigenvalues, it's the eigenvalue matrix. And then U is the eigenvector matrix. But it sure looks an awful lot like U is related to this attitude transformation matrix, right? So bear with me here. Since P is symmetric, we know U is an orthogonal matrix. And then the columns of U are normal vectors. So U is not just orthogonal, but it's orthonormal, which means it is actually an attitude transformation matrix. So what we're going to say here is U PU is equal to lambda, and that's also equal to P prime. So we're saying that the covariance in the principal frame in this case, U inverse is equal to U transpose. So then some vector Z prime is just U times Z, or in this case, sorry, T times Z. So you could think of it this way. T is U transpose, or T P T transpose is lambda, which is P prime. Okay, what am I saying? I'm saying that if you eigendecompose the matrix P, you get an eigenvalue matrix, which is diagonal, and you also get an eigenvector matrix. That eigenvector matrix is an nth dimensional attitude transformation matrix, which maps from whatever your starter frame is to your final frame. Or in this case, sorry, it is the transpose of that. So it maps from the principal frame to the final frame. And that allows us to say, okay, starting with some random covariance matrix with weird off diagonal terms, we can actually map that into something way more feasible and doable, and then kind of do our analysis in this principal axis frame. So let's do, and this is our last bit. I recognize we're over time here. Let's do a numerical example. To drive this point home. So what if I asked you to plot for me P, which is 3.25, 1.229, and then 1.229, we know it needs to be symmetric, and 1.75. How in the world would we deal with these off-diagonal terms? Okay. Well, first, we find eigenvalues and eigenvectors using, remember, the determinant of lambda I minus P is equal to 0. That's the characteristic equation of a eigendecomposition problem. And if we go through and do the math, we'll find, so if we do the math, we will find the first eigenvalue is 4, and the second eigenvalue is 1. And then we'll find the eigenvector corresponding to the first eigenvalue is 0.866 and 0.5. Sorry, eigenvector 2 corresponding to the second eigenvalue is negative 0.5 and 0.866, which these numbers should look a little bit familiar here. So from this, we can say that sigma 1 is 2, sigma 2 is 1, and T, which is the eigenvector matrix transpose, so it's going to be U1 transpose, U2 transpose. Well, that is going to be 0.866, 0.5, negative 0.5, 0.866. They should start to look really familiar. This is cosine of 30 degrees, sine of 30 degrees, negative sine of 30 degrees, and cosine of 30 degrees. So that is to say that in the principal frame, we've got a x-axis covariance of 2 and a x-axis standard deviation of 2, y-axis standard deviation of 1. That's our sigma value. But then the difference between our principal frame and our actual frame, like kind of the starter point, is this 30-degree rotation. So if this is Z1 and Z2, I'll need to pick a new color here. Maybe I'll do this kind of pink color. And here, Let's do it this way. Let's say this is U1 and this is U2. Then along U1 and U2, let's say this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. Then as drawn, our 1 sigma covariance in the principal frame goes from 2 to 1. Let's try a little better here. 2 to 1. One more time. I can do it. 2 to 1 to 2. Good gracious. All right, last attempt. Then I'm just going to kind of start flubbing it. Like that. There we go. And then that's our 1 sigma. Our 2 sigma is 4, 2 to 4 to 2 to 4. And then our 3 sigma is 6 to 3 to 6. And we'll make that symmetric. There we go. So this is 3 sigma. Green is 2 sigma. Nope. Sorry, I thought I switched colors. And then orange is 1 sigma. And in this case, we're saying, okay, in the principal axis frame, it's the same plotting problem that we had before. So we've got 1 sigma, 2 sigma, 3 sigma. But the principal axis is rotated 30 degrees from kind of our starter position. So the eigenvector matrix, and this kind of blew my mind when I learned it for the first time. The eigenvector matrix, when we're working with problems like these, is really an attitude transformation matrix, which I think is pretty slick. And that maps from whatever your base frame is to your principal axis frame. And at first I thought, oh, that's really cool. So in navigation, eigendecomposition gives you basically a core set of values, which is more intuitive, and then basically a rotation matrix, that sort of thing. And that's not the case in navigation. That's the case more generally. So I didn't really appreciate how cool eigendecomposition was until I was a little bit further through my collegiate career than I'd like to admit. But that is everything. Apologies for the extra long topic today. I'm going to try not to make a habit out of that. But today we've laid a lot of really good groundwork for our estimation theory techniques in the next 2 lectures, which is going to be necessary for homework 2. So I'm going to go ahead and stop the recording, but I'm going to stick around if anybody has any questions, either about this or about homework 1. So with that, class is dismissed, and thank you, everybody.